Good afternoon. We have a binomial expansion from IBHL to do today. This is part of a few videos that we're doing on binomial expansions. There will be a playlist. This problem is super interesting because it requires us to do two binomial expansions that are multiplied together. And this is a really challenging type of problem. We're going to have to do expansions for both of these, then multiply them, and then look at the values in the expansion to try and find a value for n. And the mistake a lot of people make when they do these problems is they do too much work. So we don't actually have to expand very far to be able to answer a problem like this, as you'll see. So I'm going to try and save you a little bit of time on the exam, a little bit of work. This problem says, given that 5 plus nx squared times 1 plus 3 over 5x to the power of n is equivalent to 25 plus 100x. Find the value for n. The big thing to notice here, when we're doing this multiplication, it's only going to be useful to us to have terms that match with something in this expansion on the right. Because all the information that we're going to use to try and set up equations for n is going to have to be equal to something. So it's going to have to be equal to either 25 or 100. And the highest power that we have over here is 100x. Almost always in this type of problem, the first number in the expansion is useless to us. The reason it's useless to us is this is just 5 squared times 1. So it doesn't tell us anything helpful about n. N is not going to be involved in that first term. The 100x is really the one that we're interested in, and that means for both of these expansions, I only care about the first two terms, the term with no x and the term with just a basic x term. So if we start by looking at these expansions, they've been a little bit generous with us here. They've recognized this is a hard problem, so we just have to do 5 plus nx squared. And if you're practiced with these, this should be pretty quick to do. So it follows that 1, 2, 1 pattern. So we're going to have 25, which is 5 squared. Then we're going to have 2 times 5 times nx. So that's going to be 10 nx. And then the last term is also going to be squared. So this is going to be n squared x squared. And this is, I think, a good demonstration of why being familiar with certainly the power of 2 and the power of 3, maybe even the power of 4 for binomial expansions is super helpful, because you can do stuff like this very quickly. And in lots of other problems, that's helpful. It saves you a lot of multiplying out for solving things. I really didn't need the n squared x squared, right? Because we're never going to have an x squared term. But it's so easy to do here, I've just done it anyway. This is the one where we have maybe some problems. And there's lots of things that are odd about this expansion. We almost always get a value for the power. They haven't given that to us here. So we're going to have to get really creative about how this works. Luckily, we only really need one term, because the first term for this is going to be 1 to the power of n. All the binomial coefficients start with 1 on Pascal's triangle. So it's just 1 times 1 to the power of n times 1. It's just 1. The first term is just 1. So I don't really care about this. This is also where the 25 comes. I said earlier, this doesn't give us very much information. And it's just because when you multiply these together, it's the part where you're doing 25 times 1. So I only care about that 100x. The next term is going to be a little bit tricky. We're going to have our two terms, obviously, are 1 and our 3/5 x. And our powers here, I mean, we started out with, presumably this is 1 to the power of n. So this is going to be n minus 1 here for the first term. And this is going to be a 3/5 x to the power of 1. So we've counted up, basically. We started out with, whatever this power is, it was 1 to the full power. Now we're going to have gone 1 down to n minus 1. And we're going to have gone up. This would have been 3/5 x to the power of 0, the world's smallest handwriting no one can read. But that was basically why we had 1 in the first term, because it's to the power of 0, now it's to the power of 1. Then what we also need, and this is, I think, the trickiest part of this problem, aside from just not panicking and and keeping a level head and working through it, is this is going to be n choose 1. So how do we work through something where we don't know the value of n? Well, if we go part by part, they resolve themselves fairly easily. So I'm just going to make this a bit bigger so we can see more clearly what's going on. We've got n choose 1 to the power of n minus 1, 3/5 x now to the power of 1. So these add up to n as they should. 1 to the power of anything is just going to be 1. So hopefully that's just 1. N choose 1, well, any sort of choose that starts out with a power and then has the 1, it's just going to be the value of that power. So like 8 choose 1 is just 8, 7 choose 1 is just 7, 9 choose 1 would be 9, and n choose 1, helpfully, is just n. And then 3/5 x raised to the power of 1 is just 3/5 x. So I think this is a really good example of a problem where not panicking at the start is really important. Because it seems like not knowing n and all of the multiplication that has to happen, that seems very daunting at the beginning. But actually, once you've expanded them out and done a little bit of work, I think it becomes clear that the not knowing the n is not as big of a problem as it seemed at the beginning. Now, there might be situations where you have to do n choose 3, for example, and we don't know what n is. So this creates a bit more of a problem because I can't just write an equivalent to n because it's not n choose 1. What would we do in that situation? Well, again, not panic too much and try and work through it. So n factorial will go on top, as is standard. 3 would be one of our values on the base, and then normally the other value on the base is the value of the power minus the other one. So here, n minus 3. These two numbers on the bottom always need to add up to n, so we have 3 n minus 1 factorial. And what we can pull here is a bit of a trick that's similar to what we've done in the past, which is to go n. What would the next term in n factorial be? Well, it's always 1 less. So this is n minus 1. The next term would be 1 less, n minus 2. And then we could do n minus 3. And here's the clever bit. We go n minus 3 factorial. So that's going to keep going. I mean, maybe there's an n minus 4, n minus 5. We have no idea how many terms there are because we don't know what n is. But we can stop at n minus 3 factorial. That's going to cover all of our bases. And then some of you might have spotted that means we can cancel there. And we get a value for n choose 3 that's n minus 1, n minus 2, 3 factorial. So any type of problem where they give you an n choose, and it's not something really straightforward like n choose 0 or n choose 1, you can go through this process to get an algebraic representation for what that binomial expression is going to be. Luckily, we don't have to do that here. I just thought, given the problem kind of hints in that direction, I'd show you how to do that. Coming back to this, which doesn't require us to do that at all, we're going to now have a pretty good expansion of our term, right? We're going to have 25 plus 10nx plus whatever comes after times 1 plus 3/5 nx and then whatever comes after. So we only really needed the first two pieces. We're trying to find our 100x. So what things are going to multiply together to give us 100x? Well, if we do 10nx times 3/5 nx, we're going to end up with an x squared term. So that's no good. What we need to do instead is we need to try and think about what's going to give us an x. So 10nx times 1, 3nx times 25. So let's multiply these out to try and find our answer. So we're going to have 25 times 3/5 nx plus 10nx. And then these are the two terms that when we multiply them together, they're going to give us all of our x's. We add them together, they should give us our x to the power of 1 term, which we were told was 100x. So if we try and work through this, we're going to have 10nx 100 So if we cancel all of the x's, that's 10n equals 100. 3/5 of 25, well, if we divide 25 by 5, we get 5. 5 times 3 is 15. So we have 15n, and the x's have been cancelled. So this gives us 25n equals 100. And if we divide those, our value for n will be 4. So by working through the first couple of terms, understanding that we don't need to go further than our x term, we're able to do this without wasting too much time, right? And actually, a lot of the things that are intimidating about the problem, with the power of n, or the fact that you've got to multiply two binomial expansions together, they're actually a lot less work than they initially seem.